Thanks very much for the organizing committee for allowing me to speak here.
You're part of the organizing committee?
Yeah, that was the joke. So this is an attempt at the synthesis of three works that I was involved in over the last year and a half. These are papers in collaboration with Efrat Gershkovitz, who is a student at Weizmann, Jaume Gomis, not a student, Poshen, Nafitz Ishtiak from the Perimeter Institute, Avner Karasik from Weizmann, Sylvia Pufu, Adam Schwimmer, Nari Seiberg, and Stefan Theisen. Some permutations appeared in these papers. So the main purpose of this talk is to revisit some problems in supersymmetric quantum filters, which were out of reach a decade ago, but now they can be solved using some more modern ideas, and one can learn many interesting things from these solutions. So the specific thing that I'm going to focus on, although this could be extended to various other discussions, so I will be focusing on the chiral ring in n=2 theories in 4 dimensions. This is, of course, a subject that was discussed in many papers in the past. What I'll do in this talk is I'll try to present a procedure that allows to make exact computations of the structure constants of this chiral ring as a function of the coupling constants in the theory. So it's a non-holomorphic observable. In some sense, the things that I'll be discussing are the simplest non-holomorphic observables in the theory. And I'll present some procedure that allows to solve for this sector of the theory. So I think that it's somewhat curious because I don't think there is any other non-trivial quantum filter in D bigger than 2 for which the structure constant, any structure constant in fact, is known non-perturbatively. And it's not a protected quantity. So it's a non-trivial function of the coupling constants. So this kind of things lead to interesting connections with mathematics. So this kind of discussions lead to interesting connections with mathematics, with the bootstrap program, with all the ideas in quantum filtering about the properties of perturbative series, and so on. So we will see all these connections pop out as we go along. Now, in some very precise sense, all this progress was sort of spurred by this paper of David and Nadav from 2001, and so there is some historic sense in which this is the starting point of all of these developments. And well, so I just wanted to wish a happy birthday to David, who is holding a poster describing some slightly less well-known discovery of David. So happy birthday. Okay, so in supersymmetric theories, let me just make, so I'm trying to define the setup. In supersymmetric theories, it's very natural to study the so-called chiral operators. So these are operators which are annihilated by all the supercharges, the right-moving supercharges, let's say. And you can say that essentially the vast progress on supersymmetric quantum field theories in the 90s amounts to studying correlation functions of chiral operators, but not involving anti-chiral operators. So what people have done in the 90s, I mean, all of these developments about the vacuum structure, the Seiberg-Witten solution, all of these things are more or less focused on computing holomorphic correlation functions of products of chiral operators in the vacuum. So that's what one can say was more or less achieved or completely solved in the 90s and the early 2000s.
So you're looking at n=1 and n=2?
Yeah, so I'll be looking at n=2 in 4 dimensions, but many of the things can also be extended to n=1, and there is also a lot of stuff to be said about 2 dimensions, but I'm just focusing on n=2 in 4 dimensions, so where one can make contact with Seiberg-Witten theory.
So this operator is annihilated by 4 supercharges?
I'm talking about n=2 in 4 dimensions, where there are 2 right-moving supercharges. There is a spinor index which is suppressed. A is an SU2R. A is an SU2R index. So the the spinor index is suppressed. There are 4 real supercharges under which they are annihilated. Indeed, so the Seiberg-Witten solution and also many analogous computations in n=1 amount to holomorphic correlation functions of these kind of things. What I'll be discussing here is in some sense the analog of MHV, in scattering amplitudes, which is when you insert many holomorphic chiral operators and 1 anti-chiral operator. So that's in some sense sort of analogous to what people in scattering amplitudes call MHV, minimally helicity violating amplitudes. So the claim is that these are the simplest non-holomorphic observables in the theory. They're not protected. And the question is, what can we say about them? So given that we have n equals 2 supersymmetry, can we say anything about it? So one trivial observation, this is just representation theory, that the dimension of all of these operators is fixed by their R charge. Okay, so there is a U1 R under which these operators are charged, and they're neutral under SU2 R. And so for these correlation functions to be potentially non-vanishing, you need the sum of the dimensions of the chiral operators to be equal to the dimension of the anti-chiral operator. So this is some condition that needs to be met for these correlation functions to be non-trivial. Okay, so this is the setup. I want you to keep in mind 3 examples so that discussion will be more or less concrete. So n equals 4 is a special case of n equals 2. And you could ask what is known about this kind of correlation functions in n equals 4. This was a very important development by these people from the late 90s when ADS-CFT came by. They conjectured that these correlation functions in n equals 4 are saturated by 3-level diagrams. That was a conjecture, and it was proven a little bit later. So in n equals 4, these correlation functions are extremely protected. They are 3-level exact, and we know them for all couplings and all n, essentially for all n equals 4 theories. So in n equals 4, these are non-holomorphic correlation functions because they depend on Young-Mills, not just in a holomorphic fashion, but they're trivial. The next example that I wanted to keep in mind is Seiberg-Witten theory, which is a genuine n equals 2 theory. It's not n equals 4. You can have in mind SU2 with 4 fundamental hypermultiplets. This is a conformal field theory. And in this theory, the chiral operators are just trace of phi squared or phi some chiral operator. Phi is the scalar in the vector multiplet raised to some power n. So this is the complete set of chiral ring operators. So what I'll be interested in are, let's say, 2-point functions of On with O bar n. And this would now be a non-trivial function of tau and tau bar, where tau is the holomorphic gauge coupling, and tau bar is the conjugate. The operator product expansion can be taken to be just that. So when you multiply these two guys, n and m are just add up. Okay, so the question is, can we determine these functions? These would be highly non-trivial functions, and they have a very interesting geometric interpretation. So the question is, do we know what these functions are? One thing that you'll see is that they are no longer saturated by 3-level diagrams, unlike in n equals 4.
The OP quotient depends on tau?
No, I'll just choose it to be 1. So I'll be using a convention. This is a freely generated ring. I'll just use a convention where this is 1. And then the question of what is the 2-point function becomes non-trivial. Or you could set the 2-point function to be 1, and then you could say that you're computing the structure constant. Okay, so the question is whether you can compute the structure constants in some normalization, where they would be non-trivial functions of tau and tau bar. Now in this theory, there is also a duality, so there is a fundamental domain. And you could ask, how does this correlation function depend on tau? One specific interesting case is the case of O1, where the operator is just trace phi squared. This is an especially interesting correlator, an especially interesting special case, because this is the Zamalotchikov metric on this upper half plane. Okay, so the Zamalotchikov metric, namely the distance between two nearby theories, is determined by the metric that's induced by this 2-point function, because these are the operators that induce marginal deformations. So if we wanted to know the geometry in this space, we could try to compute these 2-point functions. Now, of course, this is just the moduli space of tori, and there is a classic geometric theory, I mean, the Weil-Peterson story, which tells you that this should be just the metric on the upper half plane. And this is what n equals 4 would induce. In n equals 4, indeed, this 2-point function is just given by some silly power of Young-Mills, and you get the upper half plane metric. But you'll see that in Seiberg-Witten theory, that's not the case. You get a non-trivial metric on the upper half plane.
And this correlator doesn't have a disconnected part for two vacuums?
No, so this is a conformal field theory. So the 1-point functions vanish by dimensional analysis.
You look at the SU2 theory with 4.
Right. You could do many other things. That's one example to keep in mind. So here is a perturbative expansion that was, well, some of it was done before, but to this order it was done very recently by Kyriakos and collaborators. They just did the Feynman diagram computations. And in n equals 4, if you did SU2 n equals 4 theory, you would just get the first piece. So that would be the upper half plane metric of Poincaré. But here, you see that there is a non-trivial expansion with funny numbers. So the geometry that Seiberg-Witten induces on this fundamental domain is not that of the upper half plane. So it's not constant curvature. So the question is, do we know what it is to higher orders? So they did some very laborious, explicit computations. And the question is, whether we can extend it. So it's clear that this is not saturated by tree-level diagrams. Another example you may keep in mind is just SUN. This is the conformal SUN theory that Misha also mentioned in his talk. Well, Misha was talking about UN, which is not conformal. I'm talking about SUN. Here, the chiral ring is generated. Again, it's freely generated, but it's generated now by finitely many elements. So there are n-1 elements. You just take products, raise them to powers, you get the full chiral ring. And you can, again, try to compute these correlation functions that involve any number of chiral operators and at most one anti-chiral operator. Again, this specific guy is interesting. This specific correlation function is interesting because it measures the distances in the space of theories, the Zamolodchikov metric. So the two-point function of these operators of dimension 2 always measures distances. It measures the Zamolodchikov metric. But there is also a nice geometric interpretation to the other correlation functions that I mentioned. You can think about them as defining some holomorphic vector bundle over the space of moduli. And then you are computing some metric on this vector bundle. So this is something that's very common in mathematics, that these moduli spaces of algebraic curves, they have some canonically defined vector bundles, which are exactly those chiral operators. And mathematicians are interested in those metrics too. So, and physically, of course, these are as good correlation functions as any other. So one can try to see what we can say about them.
Just to confirm, the coupling constant is in the same representation as this delta.
Exactly. The coupling constant corresponds to this guy. Yeah. So the central idea that I will use to try to solve this problem is a compactification of this conformal field theories on the force sphere. The force sphere is basically, for conformal field theories, the force sphere and flat space are very closely related. It's just a technical trick. You add a point at infinity, but angles are preserved. So there is a canonical way to put any conformal field theory on the sphere. So that will be one thing. Another introductory comment that I want to make is that you would have thought that the sphere and flat space are basically the same because they're conformally related. But there are some anomalies that you have to understand. And for this talk, it will be extremely crucial to understand some subtleties that arise from the map from flat space to the sphere. I think that this business with the anomalies that I'm going to explain is why it hasn't been done before. It's extremely subtle. So let's go to flat space. Let me just remind you of some ideas about flat space before I explain the anomalies. So in flat space, you can generate all the correlation functions that you want by deforming the theory with some space-time dependent coupling constants and then taking functional derivatives of the partition function. This generates for you any correlation function that you want at separated points. If some of these points coincide, it's also okay. So we know how to generate all the correlation functions. But now, when we go to curved space, there are some ambiguities. Or you'll see that these ambiguities can also be thought of as anomalies. The ambiguities are as follows. Let's imagine, just for simplicity, that we have an operator of dimension 2, like trace phi squared. This operator would have an associated coupling tau 2. I forgot the parenthesis here. So this would be a coupling that you could add to the action just to generate correlation functions. But we can also add this term, where this is the Ricci scalar. This is okay dimensionally, because tau 2 has dimension 2, and R has dimension 2. So this is okay dimensionally. It's a good counter term. It vanishes in flat space, so it doesn't do anything to this story of taking functional derivatives. But it leads to a non-trivial one-point function. Because now that when you take a derivative with respect to tau 2, you get a one-point function, and you get the Ricci scalar. And this is non-zero in curved space. So you see that even though this is a very surprising, well, for me it was surprising, but even though these places are conformally equivalent, if you put an insertion on the sphere, like if you put an operator on the sphere, the one-point function may not vanish, even though it's a conformal field theory. And you would have thought that you can map it to flat space, and in flat space it vanishes. Even for primary operators that map, that transform very nicely under conformal transformations, it's not true that the sphere one-point function vanishes.
But these chiral triggers are charged, so it's something else.
Well, this is already, yeah, this can depend on the details. You mean charge under what? Under? Yeah, but the sphere compactification generally breaks the U1R. So yeah, they may get a VEV themselves. Even these chiral operators can get a VEV, because the sphere compactification. That's right, but to define correlation functions in QFT, you should imagine that you have regulated a theory, and there is no way to regulate a theory while preserving U1R. So these counter terms can be induced by some regulator, and they lead to non-trivial one-point functions. So there is a preferred scheme, obviously, where this is put to 0, and then the flat space and the sphere are the same. But as you will see, this scheme cannot be always chosen. So if you do, I'll explain why, but there is not always a choice of scheme for which the one-point functions on the sphere vanish. That will be a central point. So the way to think about this equation, yeah, it's very similar. It's very similar to various other ambiguities that you know. Yeah. It's like when you can mix the energy momentum tensor with a primary operator of dimension 2 by doing an improvement. It's very similar. But this leads to the breakdown of the intuition that the sphere and flat space are the same. Okay, and this is very important for what I'm going to discuss. So this is a mixing of O2 and the unit operator, but more generally you can have the O operator mixing with all the operators of lower dimension, but in jumps of 2. It's not that you can do whatever you want. The jumps have to be in 2 units, because you can use the Ricci and various other geometric invariants, but you can't just do whatever you want. Now, in non-supersymmetric theories, you can always choose a scheme in which this mixing vanishes. So in non-supersymmetric theories, there is always a scheme in which flat space and the sphere are basically the same. But in n equals 2 theories, this can be induced, but you may not be able to remove it by a local counterterm, because local counterterms have to be n equals 2. And n equals 2 counterterms are holomorphic. And this mixing may be non-holomorphic. So you won't be able to remove it, and then you should think about it as an anomaly. Okay? So in n equals 2 theories, there is, in general, no scheme in which this mixing is absent. So this mixing is completely physical, and you can think about it in the language of Deser and Schwimmer as a type B anomaly. It's a genuine new trace anomaly. There is one special case in which this anomaly was analyzed in a lot of detail. This is the case where an operator of dimension 2 mixes with the unit operator. The other cases were not analyzed. But the case where a dimension 2 operator mixes with the unit operator was analyzed in a lot of detail in one of those papers that I quoted in the beginning. And we've shown explicitly that it has to do with some new type B anomaly in supersymmetric theories that is completely physical. So while the mixing seems like a counter term, it sits in the same supersymmetric multiplet as a non-local term, where there is a non-zero imaginary part. So a genuine correlation function at separated points, not a correlation function at coincident points. So in supersymmetric theories, this kind of mixing cannot be removed because it's a partner of some non-local term. We've determined this non-local term, and there is no doubt that it exists. It also has something to do with the mathematics of Panay's operators, but it's not the main thing that I want to emphasize. So the conclusion is that sphere compactifications in general induce operator mixing in some very special way, like resonance mixing, you could say. And so when you translate computations on S4 to flat space, you have to be extremely careful about it. So in some sense, you have to use what's called the Gram-Schmidt procedure. That if somebody hands you a correlation function on the sphere, and you want to interpret it in flat space, you first have to get rid of the mixing. And getting rid of the mixing is something like a Gram-Schmidt procedure, that you want to project out these lower dimensional operators. Okay, so this is basically the idea that I want you to have in mind. So now let's discuss SU2, Seiberg-Witten theory, or n equals 4, SU2 theory. So the partition function on the sphere as a function of the coupling constants was worked out by Pestun as a follow-up to this work of David and Nadav that I mentioned. So we know the partition function on the sphere, and therefore we know the correlation functions on the sphere. But so if you take derivatives of the partition function with respect to the coupling constants, m derivatives with respect to tau, n derivatives with respect to tau bar, you can prove, and this is a highly non-trivial exercise that you can do, but you can prove that these derivatives compute for you correlation functions at separated points, where this is inserted at the north pole of the sphere, this is inserted at the south pole of the sphere, and these are exactly the chiral ring generators that I'm interested in. The fact that this is true is highly non-obvious, because you would think that a derivative with respect to a coupling constant would insert a top component which is integrated, rather than a bottom component which is localized to a point. So the fact that this identity is true is something that, well, is a very long computation in supergravity that I don't want to impose on you, but it can be done, and it's correct. So the first observation that led us to this business is that derivatives with respect to coupling constants lead to separated point correlation functions on the sphere, rather than integrated two-point functions of top components. So from the matrix integral that was worked out by Peston, we know the correlation functions on the sphere at antipodal points.
Are these ordinary derivatives or covariant derivatives?
Ordinary derivatives, standard ordinary derivatives. It's very important, standard ordinary derivatives. So the Warden entity that you can work out shows that indeed an integrated top component can be related by some manipulations that involve integration by parts to localized bottom components. But it's a non-trivial exercise to see. That's right. An ordinary derivative is not an insertion of an operator. It's an insertion of an integrated top component. But you can prove that it's equivalent to the insertion of an operator at the north pole of the bottom component. This is a non-trivial result that you can prove. I'm just giving you the result. Right, right. You have to worry about contact terms. It's a long story, but it has been shown. And the results that we get by assuming that this is true are consistent with all the non-perturbative computations from the 90s and 2000s and three-loop computations. In all.
Is this something you just discovered, or you why would you expect that?
Why did we expect that? Well, there were many reasons, but I don't think sharing them would be very good because they were not precise. The reasons were not precise, and it took time to make it precise.
So what's the reason that the anti-chiral wants to go to the south pole and the chiral wants to go to the north pole?
Okay, so let me give you some intuition of why we thought it's true. So if you take derivative with respect to tau, which is some coupling constant, you get integrated F terms, integrated top components. Now, in ordinary supersymmetric theories, the F component can be written as Q squared of some bottom component. And then you would think that these correlation functions are trivial because you take the Q squared from one integral, move it to the other integral, and so the correlation function has to vanish. So what are we talking about? The point is that Q squared on the sphere is not globally defined. There is a singularity at one of the poles, and you just choose which pole, arbitrarily. So you can use this trick everywhere except for one point. And then at that point, you have some singularity. You need to integrate by parts. You need to work around that point, which is singular, and you can show that this is what you get. It's a non-trivial regularization procedure of what happens at that specific point where the supercharge doesn't exist. It has to do with the fact that there are no spinor bundles with non-zero sections on S4.
So the difference is that Q bar is sick.
Yeah, there is one point where Q bar is sick. But then you have to work very carefully to see what happens at that point. And after some work, this is what you get.
Is the same applicable to n equal 1?
We'll discuss. I can discuss n equals 1 at the end. It will take me a little bit
Okay.
outside of. Okay, so let us work out an example. The simplest example is the Gram-Schmidt procedure for operators of dimension 2, which measure distances, like the Zamolovchikov metric and the unit operator. So we have the full matrix of two-point functions on the sphere, where the zeros operator is just the unit operator. So the unit operator in the sphere is just Peston's partition function. That's what Peston computed. This is this Z of S4. Now this guy is one derivative. This guy is one anti-holomorphic derivative, and this guy is a double holomorphic anti-holomorphic derivative. These are just S4 correlation functions. But I told you that there is an anomaly. You can't go from these correlation functions to flat space correlation functions. You would get nonsense if you tried. You need to do a Gram-Schmidt procedure. Gram-Schmidt is basically taking determinants. Okay, so if you have a matrix and you want to perform a Gram-Schmidt procedure, you take determinants of some submatrices. So the correct flat space correlation function, this is R4. So this is flat space now. So I'm talking about Seiberg-Witten theory now in flat space, and these are the marginal operators in Seiberg-Witten theory, is given by the determinant of this matrix. That's how you do Gram-Schmidt. You take determinants. The determinant of this matrix happens to be the second derivative of the log of the partition function. It's just a trivial identity, chain rule, okay? And therefore, the S4 partition function is an exponential of the Kähler potential. This is a rederivation in this new language of a result that we established in one of those papers.
Technical comment, the Gram-Schmidt that I know is done by taking dot products, taking orthogonal components, not
Right.
by taking
It's equivalent because if you know that any vector mixes only with vectors, so if you have some ordering, in Gram-Schmidt procedure there is always an ordering, right? You have to decide what you do first. So if you know that, well, once you establish this ordering, then the norm of the vector after the Gram-Schmidt procedure is given by ratios of determinants.
somewhere you have to put in the inner product of the list. Maybe it's not an important point.
Yeah, surely it's this is correct, yes? Okay, so the force sphere partition function is an exponential of the Kähler potential. That follows from this idea about mixing with the unit operator. Now this funny result that the sphere partition function computes an exponential of this, the Kähler metric in Seiberg-Witten theory has lots of consequences. One consequence that we worked out is that it has consequences for topology because K is not quite well defined, so you could object to this formula. Because what is K? K depends on the Kähler frame. But that actually leads to an interesting consequence that the Kähler frame, so the Kähler 2 form has to be trivial in every physical theory. Every physical four-dimensional theory, the Kähler form has to be trivial, otherwise this formula would make no sense because you would have to do Kähler transformations when going from patch to patch. So this can be checked. It's some topological constraint on what kind of spaces of theories are allowed. So so basically, if you want to remember this result in some vague or in some not completely correct way, you could say that there cannot be any cycles, two cycles in the space of theories. So the space of theories, the space of quantum field theories cannot have two cycles because otherwise there would be some flux of the Kähler form, and the Kähler form would not be well defined, and the Kähler form would not be trivial in the cohomology. This also, due to the fact that this has a nice expression in terms of a matrix integral, this can be used to compute the distances in Seiberg-Witten theory, a non-holomorphic observable. So I just quoted for you the instanton contribution. So the perturbative contribution was worked out by Feynman diagrams. You can see they agree. This is also just for the sake of showing that it can be done. This is an instanton contribution that we now know exactly. It's not part of the Seiberg-Witten solution, but now we know it exactly. Mathematicians call this kind of deformed metrics a quantum-type Mueller theory, but I don't want to get into it. Now let's.
Z is on the sphere.
Right, and it computes.
The metric is on the flat.
That's the magic,
And
yes.
there is an exact relation.
Yes. This is what I proved. Well, I explained, yes. And you can use it to compute the distances in the space of theories. Okay, now.
So this means that Z of S4 doesn't depend on the radius of this S4, right?
It depends, but in a very weak way, just through the A anomaly.
Okay.
So this formula is actually not complete. This is for radius 1 sphere. If you introduce the radius, you have R to the power A anomaly. So you have to subtract it. But it's trivial. It doesn't depend on tau because the anomaly doesn't depend on tau. It's an anomaly, so it's easy to subtract. So this procedure actually generalizes to the full chiral ring of Seiberg-Witten theory. You get ratios of determinants. Okay? Because the Gram-Schmidt procedure works like that. So one can determine in flat space all the two-point functions of chiral and anti-chiral operators. These are non-holomorphic observables, and you get ratios of determinants of the sphere partition function. So it's not e to the k, it's something slightly more complicated, but still very compact. Now, as I'll explain very soon, such ratios of determinants appeared in the theory of integrability just 15 years ago or 20 years ago. People discovered that when you have ratios of determinants of derivatives of some function, you have integrable systems. So, and I'll also mention that one can prove that in every n equals 2 gauge theory, the set of chiral, anti-chiral correlation functions leads to an integrable system. It's a general fact that I'll explain a little bit more.
Zohar,
Yes.
does one have to worry about this change in this disposition value of the 100 yes circular with some?
Say again?
So Weizmann famously in his paper computes this partition
Right.
value of the circular with
Right.
some. That's of course the way he did it was this partition value of the sphere.
Right.
Is
Oh,
that-
you're
is
asking
that
if
the
there's.
same as this partition?
You're asking if there is an anomaly in going from the sphere to flat space for Wilson loops. That's something that's on the to-do list, but I don't know the answer at this point. I mean, clearly in n equals 4 there isn't any because
But that was very simple.
I just don't know. I mean, I believe that there could be anomalies also for extended objects, but I don't know how to characterize them. I just don't know. For this, the problem is solved. This is the result. Now, as I said, when you have derivatives of some function, you get a Toda chain. And this is basically very similar to what you get in Tt-star equations in 2 dimensions, and Kyriakos took the 2-dimensional Tt-star equations and rewrote them also in 4 dimensions. And so you would expect that something like a Toda chain would appear also in 4-dimensional Yang-Mills theories, because there are Tt-star equations which often lead to Hitchin systems or Toda chains. But here you can see it explicitly. So the set of correlation functions, so if you look at G2M, this set of correlation functions obeys some intricate set of differential equations which are isomorphic to a spin chain or a chain of oscillators, something like this, with some very particular force. Okay, so it's a formal observation, but it's useful because it allows you to solve all of them immediately. So there is an integrable system that hides in Seiberg-Witten theory that describes all of those correlation functions. You can use that to compute whatever you want. I will show maybe a little bit more results soon. But since this is explicitly known, you can put it on the computer, compute any correlation function that you want, including instantons to arbitrary precision, and to any number of loops. And in fact, we did some resurgence analysis showing that it's an asymptotic theory, asymptotic series, with Borel poles on the negative axis, as you would expect. And there are some other formal properties of resurgent series that you can actually check very explicitly using this result. Okay. So it's a very general fact. You can prove that every n equals 2 gauge theory gives some integrable system for this set of extremal correlation functions, namely any number of chiral operators and one anti-chiral operator. So unlike n equals 4, they are not tree-level exact, but they give rise to some integrable systems, and we can in principle solve all of them now. And you can make comparisons with ideas. There are many applications. I'll get to the application soon. Now, the special integrable system that appears in n equals 4 for any gauge group consists of infinitely many decoupled Toda chains. So it's a pretty simple integrable system. But if you look at super QCD, not SU2, which is Seiberg-Witten, but if you look at SUN, you get a more complicated integrable system. You don't get Toda chains. You get a slightly more complicated system. So following this Gram-Schmidt procedure and these general ideas about anomalies and derivatives of partition functions, I just quoted here the first few terms in the expansion, the perturbative expansion of trace phi cubed with trace phi cubed in SU3. This is an SU3 gauge theory. You can work it out. You can try to find the integrable system. You find the Hitchin system, not a Toda chain, but it's still a system that's very familiar to mathematicians.
It's still conformal, right?
Yes, this is SU3 with 6 flavors. You can work it out. I mean, the expression exists, and everything is known about it in principle. And it can be also contrasted with perturbative computations. So in some sense, the problem of extremal correlators is solved. Maybe there are some little holes that would be nice to fill for non-Lagrangian theories and so on. But you can prove that for any n equals 2 theory, there is an integrable system. In the simplest cases, such as SU2 gauge theory, Seiberg-Witten theory, and n equals 4, we get Toda chains. Otherwise, we get more complicated systems of Hitchin type. You can study resurgence theories. You can study the asymptotic properties of these perturbative expansions on the computer. It's very easy to go to very high orders and make interesting tests of various ideas about resurgence theories. Because, I mean, there aren't any other correlation functions that are known to all orders. So you can make tests of various ideas, such as Dyson's arguments and so on, very explicitly. And you can see that it works. There are many applications for idea safety, large n. So the large n limit of this kind of correlation functions is interesting for the same reason it was interesting in 98 in n equals 4. So one can get exact results as a function of the 't Hooft coupling for the structure constants. There are many applications that we're pursuing. This can be essentially repeated verbatim in 2-dimensional 2,2 theories. So the same idea about anomalies is still true. It's still true that z is e to the k. And one can use that to solve for the full chiral ring in 2-dimensional theories. And in fact, one easily reproduces all the known results from the 90s that arose from these Tt-star equations. So one can more or less immediately reproduce all the known results about the chiral rings of 2-dimensional theories. And in fact, one can compute many observables that were not accessible in the 90s, because in the 90s, many of these observables were computed only when there was mirror symmetry, when the mirror dual was known. But we don't need it now. So one can just do these kind of things and find all of these correlation functions as a function of the complex and scalar moduli of Calabi-Yau manifolds. I mean, finding the Gromov-Witten invariants of many spaces that were not reachable before. There are also many open questions. For example, the AGT-like interpretation of this business. What do these anomalies mean? I mean, these new anomalies, we haven't quite classified them. We just understand that they must exist, but we haven't understood where exactly they arise from. To characterize better these integrable systems, some applications for ADS-CFT. To determine the instantons in SUN, it's still an open problem. The omega background in SUN is still not very well understood. So there is some technical open problem that would be nice to address. So these are some of the open questions that we're pursuing. And that's it. Thanks very much.
If we want, let's say, to go to n equal 1, which is most likely non-conformal,
Well, it may or may not be.
can we preserve at least some of these achievements?
Okay, well, some can definitely be preserved. So for example, one thing that obviously holds is the following. So this is a major simplification that still takes place. So I haven't mentioned that, but you can study in general these products of chiral operators and one anti-chiral operator, an arbitrary product. I have only talked about two-point functions. But actually, if you know the two-point functions and you know that it's a freely generated chiral ring, you know all of those. You can prove it. That all the extremal correlators are fixed in terms of the three-point functions and two-point functions because you can just OP the chiral guys and you don't have singularities. So this is still true in n equals 1. Another thing that's still true in n equals 1 is that there is operator mixing, which is likely still physical. I mean, it's still something that cannot be removed. Although I'm not 100% sure about it. And the relation to the sphere partition function would still likely be true because the spinors are very similar. So I think some things can be carried over. I'm not sure exactly. Localization, of course, is a different, but for many of the results that are derived here, localization is not important. For example, to see that you have a Toda chain, you don't need to know Z. You just need this structure. Even if we didn't have Peston, you could still prove that there is an integrable system because of this structure. This structure immediately leads to a Toda chain. So you don't need to know the partition function to do many of the things that one can do. Sorry. Yes, Arkady? You get non-trivial consistency conditions, and that is certainly true. I have not explored the question to what extent it can be fixed. For example, one open challenge, indeed, for example, the partition function, the instanton part in SUN is not completely known because the omega background for this gauge theory is very hard. Well, Nikita is here, maybe he can correct me, but I think it's not known.
You should just say that it's one for UN, it's one.
You need to decouple the U1, but it's very hard. I mean, in the presence of higher Casimirs, that is what we need here, it's very hard, it's not known. So, but one has various consistency conditions from these integrable equations. It leads to non-trivial consistency conditions. So I think when to some extent one can determine some parts. I don't know to what extent. Yeah.
Is this a starting? I mean, you did analog.
MHV. Well, I don't know. I mean, the barrier from MHV to non-MHV in amplitudes has been formidable. I can't commit that there is anything I would be able to say about non-MHV. I just can't commit that it would be within reach.
But it looks like using what you use,
I just don't know. I can't say that it's possible. It's too much to ask to get all of them from localization, I feel. This is sort of, this looks benign. And
is there any chance of computing these things in non-Lagrangian theories? So therefore, there was numbers,
yes.
but still there was
Yes.
numbers.
In fact, one of the exercises that we did right after the structure became apparent was, well, you mean non-Lagrangian theories where by this, I guess you mean that the sphere partition function is not known.
Yeah.
Well, so these integrable systems can still be achieved. I mean, you can still determine them because, I mean, it's just derivatives of something that you don't know. But in fact, using the duality between non-Lagrangian theories and two-dimensional WN models, or two-dimensional CFTs, in some cases it's known. For example, for the E6, it's known. Even though E6 is not Lagrangian, we know what the answer is, so one can still use that. So for some non-Lagrangian theories, the answer is certainly to the affirmative, but I don't know. For example, in the trinion, I don't know if it would be easy. Yeah.
If you go to, say, an Argyris Douglas point, could you use this to get information about the spectrum of dimensions that we didn't know before?
I don't know. I don't know. I mean, I'm talking about chiral operators. So the chiral operators are known.
Nothing is going to come in there.
Yes, the chiral operators are known. I mean, in these two-point functions, the interesting object is the normalization, which is some non-trivial function of the coupling constants. These are like structure constants. I don't know what you could learn beyond the sector of chiral operators. You could maybe, I mean, for Higgs operators, of course, there's a lot of independent work by Leonardo and others. So, but there it doesn't depend on coupling constants. These are just numbers. Yes?
Sorry, this pointer that I lost you at something elementary, but sorry. I understood you computed these correlation functions of those operators that were related to the coupling constant by differentiating with respect to tau.
Oh, no, not just those that are related to the coupling. All the chiral ring.
Yeah, how did you get the ones that were not the coupling constant?
Yeah, I haven't explained it, but I mentioned one example of that sort.
The phi cube, right?
Right, how did I do that? So you deform the partition function of SUN gauge theory by tau 3 phi cube. It's an irrelevant operator from the quantum field theory point of view, but you can just view it as a generating function for correlation functions. You don't have to worry about the convergence. And then you localize it. So for
SU3 or for U3?
right, so for if you just care about the perturbative series, it doesn't matter because we know the small instantons don't matter. So you can do it for SU3. Yeah, you could. So this is for SU3. This is not U3. This is the conformal SU3. It's something that you can actually check in perturbation theory, in the conformal SU3 theory.
So you generalize Peston's formula.
Yes, you need to generalize Peston's formula. I didn't explain that, but we did it. You can generalize Peston's formula, but some aspects of the omega background in these generalized theories with irrelevant operators are still not known. So if you ask me what are the non-perturbative contributions to this, I wouldn't be able to tell you yet, but we're working on it.
And in the SUN theory, you have an n-1 parameter.
Exactly. Sorry. Yes, you generalize the partition. You generalize the Lagrangian by adding higher Casimirs. You localize it, which we did. It's pretty easy. So you need some generalization of Peston, and then you go. Yeah.
So I mean, if you actually do these things with localization, there is a difference between trace phi, for U2, there is a difference between trace phi to 4 and trace phi squared.
Sure.
So how do you do that?
Right. So the chiral ring is. So let's talk about SU2, right? So the chiral ring is generated. Sorry, I'm trying to go to some slide. Yeah.
ON times OM is
Right. This is what I was going to. This is what I was looking for, but I can't find it now. Okay. Oh, I don't know. Let me not look for it. So in SU2, the chiral ring is generated by trace phi squared to some power. And you have to have an a priori definition. Trace phi squared is completely well defined by the Lagrangian normalization. And then the others are defined by having a unit OP. So I define trace phi squared by saying that the OP has this operator with unit coefficient. The operator trace phi to the 4 doesn't have an a priori definition. In classically, it's related by Schur polynomials to lower operators, but these relations may be modified quantum mechanically. I don't care about these operators because they don't appear in the OP for me. So my OP is defined to be such that trace phi squared to the power m, trace phi squared to the power n defines trace phi squared to the power m plus n with unit coefficient. And in this way, I have an a priori definition for the full chiral ring.
So it's not obvious that that definition is the one.
But this is exactly the definition that this definition you can prove is exactly what this computes. So you can prove that the chiral ring relation that follows from this ansatz is such that trace phi squared to the power m times trace phi squared to the power n is trace phi squared to the power m plus n with unit coefficient.
What happens if you turn on mass?
Well, that's okay. So at the conformal point, I think that the issue is settled. There is no issue with trace phi to the 4. If you turn on masses, There may be interesting applications that we can discuss, but I don't know exactly how to start. Because in the CFT, I have an a priori definition of what I mean by trace phi squared to the m. I don't need to discuss these classical relations that are perhaps modified. There is an OP. Now, when you turn on masses, you have to be slightly more careful. And
I think we're talking about two different things. One is trace phi square versus trace phi square 1 bit.
right, right,
That's what you're talking about.
right,
He's talking about trace phi to the 4th
right.
and how it is related to trace phi.
Well, I think it's not.
What it is.
I think it's not well defined.
Modification, it's fully understood.
Right, right.
In this thing, there was
I have.
modified.
I think Zohar is saying, he said classically we understand what the
Yeah,
relation
yeah.
between two objects, but
Right.
it's modified by
Right.
No, the object you're talking about is modified by the
Right.
I understand. He's talking about something else. The
Yep.
object needs the definition.
I have.
You can
Yeah.
see the modification of the
Right. So I have a definition for what this one means by this operator somewhere, but I can't find the slide. Yeah. So the definition that I'm using is somewhere here, but I won't be able to find it obviously. Yeah, here it is.
Since the partition function of the sphere is actually essentially norm squared of the partition function omega by gram to the homomorphic object.
Yes.
So this is a
Well, it's integrated.
it's norm squared.
Yeah.
Norm
Yeah.
involves integration.
Yeah.
It's defined by a homomorphic object.
Right.
Determined by homomorphic
Right.
object. So it is a this Chiral anti-Chiral relation function is actually determined by homomorphic object.
Well, not quite. You see that they have a non-trivial perturbative series.
Because that's due to the homomorphic object. It's like usually simple dimensions, like a whole blocks, out of which you get log homomorphic relation function.
Right. But it's a sum over holomorphic blocks, so you can get non-trivial. Yeah. Right.
So, but
Indeed. It's like.
structurally, it is
Yeah, it's like in 2D that you can get non-trivial correlation functions from sums over holomorphic blocks.
It's like it means that there is some secretly there is a supersymmetry which is preserved by these two operators.
But not Poincare supersymmetry.
Not comparison with
Right.
others.
It's non-holomorphic. Yes, it's non-holomorphic because there is no this correlation function from the point of view of Poincare supersymmetry is non-supersymmetric.
Right, I mean, this supersymmetry looks like omega background
Times omega bar, right.
South pole, and so it's
But there is no globally, yeah, there is no global preserved supersymmetry. But indeed, it's sufficiently close. It's sufficiently close to being supersymmetric in some sense.
not by sphere.
Right.
There's also a version of that which is for the ellipsoid.
Right.
If you do it on the ellipsoid, what points
You would be able to insert into these things that I computed energy momentum tensors. This we have shown with a frat in some paper. So, for example, for this Wilson line of Drucker-Gross, we showed that if you look at the squashed sphere, it introduces a cusp. So you can compute the cusp Wilson line from localization, which is something, there is a lot of work on the cusp Wilson line in n equals 4, but we showed that in n equals 2 it can be also completely solved using localization by this idea of doing an ellipsoid.